Hey guys, how's it going? So today we're going to be talking about the next thing, kinetic molecular theory. So last time we talked about ideal gas law and how gases are supposed to act, um, and this is going to kind of show us why they act the way they do. What we're going to do now is kind of focus in on those representations, those pictures, to try to help us understand what is going down in Molecule Town. So let's talk about what it is that we are going to be learning about today. We're going to be looking at those particles. So this is going to be us drawing those pictures or um, looking at those little circle diagrams where you have a box and you draw circles. And circles represent atoms, all of that jazz. So we're going to talk about that, and we're going to put those guys into motion, and we're going to change things and see logically how do those particles change. We're going to talk about the fact that temperature equals motion, and we're going to look at then we're going to graph these things out and see how does the graph change whenever you change up various things. Kinetic energy in gases. Remember that anytime we are talking about temperature, whenever we're talking about temperature, we're talking about things in motion. Now, if something is solid, it doesn't have very much motion. All it has is that vibrational motion where it's vibrating back and forth. If it's a liquid, those intermolecular forces aren't as strong, so it allows the molecules to rotate independently of each other, but they're still a little sticky. So that's what gives liquid that flowy uh, property. And then gases have rotational, vibrational, but also translational motion. They can move from one location to another. So that's what you see here. You see all of these little particles. You can think of these as gas molecules, gas particles, flying around all over the place, bouncing around and off of the container walls, but also bouncing off of each other. Now, there's a couple of things that you need to think about here. And the first thing is these guys are not all moving at the same speed. They have different amounts of kinetic energy. This is why they're colored differently. Look at one of the red ones. You can track one of the red ones, and you can see it's fast, slow, fast. So it changes from fast to slow based on other particles hitting it. Kind of think of it like a billiard ball table. Whenever you break, they're all flying all over the place. Some are moving fast, some are moving slow. They're exchanging that kinetic energy. Now, not only are they exchanging kinetic energy with each other, but they're also exchanging kinetic energy with the container wall, this barrier. Now, that is where we get pressure from. Pressure is the amount of force that's applied to the barrier wall. You can think about this as how often and how hard the particles are slamming up against the wall. That's what pressure is just particles slamming into a particular thing. One thing that I'd like to think about is, or one thing that I try not to think about too much, is the fact that I'm under a certain amount of pressure right now. I may not feel like it, but that's because I'm used to it. Uh, and it's because all of these air molecules are slapping up against me constantly. I am constantly being bombarded by a whole bunch of different air molecules. All of them are hitting me, slapping me across the face constantly. And I'm used to it, so I don't notice. Think about that. Now, so that's what pressure is. The how often and how hard particles are slamming up against the side of a container. Okay, so that is kind of a basic idea behind kinetic molecular theory. These molecules are moving, they're hitting each other with a certain amount of force, and that motion, that total kinetic energy, is their temperature. Temperature is a measurement of how much kinetic energy these particles have. So, what happens if we change something up? What happens if I take this container and I stretch it out? Well, that means that if the pressure stays the same, the frequency and the force of the particles hitting the container stay the same, then and if I stretch out the volume, that means one of these balls is moving faster. One of these particles is hitting, or these are both hitting at the same speed, one, two, same frequency. So the pressure is the same. This right side is a larger volume. That would mean that this particle has to be moving faster. It has more kinetic energy. And so if it has more kinetic energy, that means the temperature is going up. That's one thing, one relationship we see. And that's true. If we increase the temperature, that means the volume is going to get bigger. If I increase the volume, that means the temperature is going to go up as well. Now, let's talk about this scenario. What happens if I change the volume? What's going to happen and keep the temperature the same? So these balls, these particles, are all moving at the same speed. But if I increase the volume, if I make this box get larger, that means they're not hitting as often. If they're not hitting as often, that means that the pressure is going down. If I decrease the volume but keep the temperature the same, they're hitting more often. And since they're hitting more often, the pressure is going up. So that is kind of what KMT is all about. It's a way of imagining what's happening down in Molecule Town. So those are some examples of the visual representations we can use to help us with that ideal gas law. Calculating kinetic energy. How do we go about calculating kinetic energy? Some of you guys that have taken physics probably already know this, but kinetic energy is 1/2 times the mass times the velocity squared. So the speed squared. Okay, so how does that help us? What does that mean? That can help us determine its temperature. So before I was saying that that temperature is how fast things are going, how much motion they have. That was not quite accurate. Sorry, I lied to you. Remember, science is just a long series of me lying to you until it gets too complicated, and then I tell you the truth, and then you find out that was a lie, and so on and so forth. So here, temperature is the kinetic energy, and the kinetic energy is based on two things. The first thing is the velocity, the speed, and that makes sense. Kinetic energy is all about motion. The faster something is going, the more kinetic energy it has. Makes sense. The other thing you need to think about isn't just how fast something is going, but how much mass that thing has. A great example of this would be, if I am trying to stop a baseball rolling at 2 miles an hour, I can easily catch it and stop it in my hand, no problem. Except for catching it, I'm not that athletic, but if a shipping container was rolling down the street at 2 miles an hour and I put my hand out, I am going to the hospital because it's going to crush me. It will not stop. But they were both moving at the same speed. That means they have similar kinetic energies. No. The difference is their mass. The more massive something is, the more kinetic energy it has. So those are the two things you need to think about whenever you're thinking in terms of kinetic energy. So look at the mass of the thing and look at the velocity of the thing. How fast is it going? How big is it? That is going to give you an idea of the kinetic energy. Now, of course, if they give you some numbers to go along with this, they give you a mass, they give you a speed, you should be able to calculate kinetic energy. That's, basic algebra. I'm not going over that. But I want you to start thinking about things if I give you a graph and I say that the average kinetic energy of helium, so you're going to need to know how to use this in terms of graphs. Can you go through and make sense of this without numbers? So let me kind of show you what I mean by that. Let's have a graph, and on the y-axis, we're going to put mass, and on the bottom axis, we are going to have velocity. And let's say somewhere on this graph is helium. Okay. And I want to know where on this graph would we have a the same number of moles. This is 1 mole of helium. If I say we have 1 mole of H2, hydrogen gas, and it's at the same temperature. So, same temp. Same temperature. Where would this be? So we can think about this we can think about this kind of systematically. Okay, we need to know what's the mass difference. Is the mass of hydrogen gas larger or smaller? Well, if you for that, you can just look up on the periodic table. I can let you know hydrogen gas is about half that of helium. So it's about half that of helium. So I know it's going to be somewhere here on this line. I don't know what its velocity is going to be. But what I do know is that they have the same kinetic energy. And if I decreased the mass, if the mass of my second state is lower than that of my original state, in other words, my mass of hydrogen is less than helium, then that and the kinetic energy is staying the same, my velocity has to be going up. So I must have a higher velocity than that of helium. So my H2 should be roughly here because it's less than helium in terms of mass, and it's going to be moving faster than helium because it has the same kinetic energy, because it has the same temperature. So those type of logical conclusions are what you need to be able to get to using this particular formula. Next thing, we're talking about graphs. One thing that you need to think about is that these, just like this picture, all of these particles are not moving at exactly the same speed. Some are moving slow, some are moving fast, but their average kinetic energy is what we call the temperature. If we looked at the average kinetic energy of all of these guys, that is what we see or what we perceive to be temperature. But in truth, it's not nearly that cut and dry. Some are moving really slow. So down here, we have a small number of the particles that are moving really, really slow. Some of the particles are zipping along super quickly, and most are kind of in the middle here. So we get this distribution, and distributions are great. They kind of show you what really is happening here. I absolutely love distributions because they tell you a lot of information pretty quickly. Now, here is an example of just one state, one scenario of oxygen molecules. This is how many oxygen molecules have each velocity. So there's very few that are moving slowly, very few that are moving fast, and there's a lot in this middle. Here's the thing. If I were to increase the temperature, if I were to take this and put it under a Bunsen burner, I would be changing the average kinetic energy, but there would still be some that were slow. It would look kind of like this. The average increased, but there's still some that are really slow. And there are some now that are going super fast. So that is kind of what's happening. It's shifting this distribution over. It's not shift is not even the right word. It's stretching this distribution out. And you can continue to think about that if you like here with nitrogen, for example, whenever it's at room temperature, 273 Kelvin, it has this type of distribution. If we increase the temperature, it is now more stretched out. It's smaller because some particles are moving faster, some are moving slower. If we increase the temperature even more, it flattens out even more. The thing you need to think about is that the area underneath these curves, these areas are all going to be equal. So the area under this curve is going to equal the area under the green curve, is going to equal the area under the gold curve. That's because the number of particles didn't really change. So this is going to kind of help us understand what is happening. We can put these two skills together, looking at that kinetic energy formula and apply it to these distributions. So, for example, here we're talking about, let me just write it again, kinetic energy equals 1/2 mass velocity squared. Okay, so here's the thing. We have the same sample of nitrogen. We have the same sample of nitrogen, which means that the mass is not changing at all. But we said that we are increasing its temperature. We're increasing its kinetic energy. Remember, kinetic energy is two things. Remember, kinetic energy is temperature, and kinetic energy, or temperature, they're the same thing, is made up of two separate things, mass and velocity. In this case, our mass isn't changing. So if I'm increasing the temperature, increasing the kinetic energy, the velocity has to be moving up. So that means that this average velocity shifting up. It's increasing. Now, the area under this, the number of particles, is not changing. So that means that if I am shifting up the average, this distribution is going to have to get a little bit shorter, and the average, the peak of this distribution, is going to move up. Okay. Now let's think about this. I'm going to use this same. Thing in terms of mass. Let's say this green here is oxygen gas. Okay, and we're going to say I want to know where is methane. We have methane. Is methane at the same temperature going to look like the purple or the gold? So we need to think they're at the same temperature. Okay, we know that the O2 weighs a certain thing. It's about 16. And we know methane weighs something. It's about, so we know that oxygen weighs something. Oxygen gas, O2, is going to weigh about, 32? And the methane here is going to weigh something else. So it's going to be about 12 plus 4, 18. No, 16. Sorry. So it's going to weigh about 16. So this is going to have less mass than oxygen. So we can kind of think about that again. If the 1/2 mass velocity squared, if we are decreasing our mass to get to methane size, and the kinetic energy stays the same, velocity has to increase. So we need to be down here. This is going to be our methane. Okay. Hopefully that made sense. So that's all I have for kinetic molecular theory. And I will see you guys next time.